series. So this is the OAR 2025 Outstanding Scientific Paper Library Seminar Series. I'm Katie Poser, the Outreach Librarian for the NOAA Library, and delighted to be introducing the authors who won this Outstanding Scientific Paper award. So the award was established by OAR to celebrate the incredible science that OAR employees and affiliates are producing, and we are really excited to recognize them informally because there was a formal celebration this past summer, but we're getting more into the details now. Our next presentation is going to be, let me pull this up. Okay, global seasonal forecasts of marine heat waves. We're switching from the polar Arctics down into those marine heat waves with Michael, I didn't even ask you how to pronounce your last name, so you might have to save me here. But Michael Jacox,
Jacox, yeah.
Jacox, okay. Research oceanographer who's working double duty with the Southwest Fisheries Science Center and NOAA's Physical Sciences Laboratory. And I'm going to turn it over to you, Michael, to kick this off.
All right. Thank you very much, Katie. I'm actually going to just pop on to say hi, but I'm going to turn my camera off and hope that stops it from blocking my slides. And this certainly is a switch in topic and location from Dan's talk, but I think is similar in that it's something that we don't see every day, but whose impact is becoming more and more apparent, and we will be confronted with it. So I'm going to talk about heat waves in the ocean, marine heat waves, and our efforts to predict these events. So what you're looking at here is visualization of ocean temperatures in the Northeast Pacific Ocean relative to normal. And anything sort of orange, red, and pink is warmer than normal, with the pinks getting more and more abnormal. And this image is from 2015. So in 2013, in the winter of 2013, 2014, this heat wave started in the Gulf of Alaska. It was nicknamed the blob because it did look in these kinds of images like a blob of extremely warm temperatures. And over the next couple of years, it spread to look like it does in this image. It covered about 10 million square kilometers of the North Pacific Ocean. That's equal to the entire landmass of the United States in terms of area, and gave us the warmest 3-year period on record from 2014 to 2016. And this has become, I think, globally the poster child of marine heat waves. So they are not all like this one, but it really woke us up to the potential suite of impacts that these events can have. And just to walk through some of those, I mean, one of the more conspicuous impacts that we saw really quickly was species showing up where you do not expect them to be. These are a couple of examples: hammerhead sharks that were over 1,000 miles north of where one might expect them. On the left, this is an image illustrative of the extremely productive sport fishing off Southern California, where things like bluefin tuna were just in abundance close to shore and also relative to what would be expected in that area. But, not all good news, certainly. There's a lot of changes at the base of the food chain. So starting even smaller than these images, the microscopic phytoplankton, they tend to be inhibited during marine heat waves because nutrient availability in the surface of the ocean is reduced. So we see lower availability of phytoplankton, of zooplankton like krill, and of the small forage fish that ultimately are the food for much of what's in the ocean. We also see a degradation of habitats. So here on the right is showing a kelp forest, sort of before and after of sort of rich and lush kelp forest turned into urchin barrens. We have a combination of direct oceanographic impacts on things like kelp, but also more complex impacts on like sea star disease being exacerbated by warm temperatures and contributing to this shift to an urchin barren. There was a record coast-wide bloom of toxic algae. This was an event, it was unprecedented. And basically these phytoplankton producing toxin are filtered through the food chain and can cause sickness and death either directly in the animals in the ocean or in people who might consume them. So this causes closures of fisheries, for example, shellfish fisheries especially, to avoid consumption and public health concerns. And then direct impacts on the more charismatic marine species. So here's one example, the common murre, which is widespread along the West Coast and in Alaska. And it's estimated that up to 1 million of these birds died during this event, which is far outpaces the Exxon Valdez oil spill, for those old enough to remember that event. And the cause is starvation. So just leading from what I mentioned earlier about impacts on the base of the food web, you have not enough food to go around, not enough food to go around, and also higher energetic demands with especially warm ocean temperatures for things living in the ocean. So impacts on birds, impacts on whales, sea lions, and then much more complex interactions that were real surprises to us, where these sort of factors, a confluence of these factors can cause impacts that we don't see coming. So here, what's going on is in the top, this is an image of, it could be an image of temperature anomalies. And what you see is this band of blue and purple along the West Coast. That's cold water that's produced by this process of upwelling that happens along our West Coast. So cold, deep, nutrient-rich water comes to the surface, and it really fuels the biological productivity of the system. During the heat wave, we see that cool, rich, productive water really compressed close to the coast. And so things that might track that cool, productive water in order to find food, like a humpback whale, are coming much closer to the coast than you would normally expect them to, and putting them in conflict with fisheries that are operating near the coast. And so we saw a big spike in 2015, 2016 of whale entanglements along the West Coast. And then impacts on fisheries. So if the fish are being affected, the fisheries are often also being affected. And so across these years and in subsequent years, we've seen fishery disasters spanning all the West Coast states and across multiple species. And then last, again, sort of flipping it to positive impacts in terms of, at least from the perspective of individual species. Since 2017, we've seen this massive boom of anchovy off the West Coast. And this picture on the right is not immediately obvious, probably, but surrounding the blue-green water that these surfers are in, that dark is anchovies. That's not the ocean bottom or something like that. That is a cloud of anchovies. So here's a quick walk through some of what can happen with marine heat waves. And this is one event, but these events happen all over. Actually, by definition, marine heat waves happen everywhere. They're not all they're not all created equal in terms of their impacts or their size or duration or anything like that. But they do happen everywhere, and they've been more and more being documented in terms of their impacts on the ocean and on human communities depending on the ocean. So you're not at all supposed to digest this slide. You're just supposed to take from this that there are heat waves happening all over the place, and there's a lot of stuff going on associated with them. This paper put the economic impact of these marine heat waves on the order of $1 billion a year at this point. Okay, so all of this that I've said is our motivation for this study. Obviously, there are impacts. Obviously, we would like to mitigate a lot of these impacts. And so can we predict marine heat waves to help with that? And the quick answer that is yes. In a lot of cases, we can. And I'm sort of jumping to the end here of the ultimate outcome of this paper, which was to produce the very first global operational forecasts of marine heat waves. So these have been available online since 2022. I've put a screenshot here of the latest marine heat wave forecast. So here you see a map of the entire global ocean. And the yellows are high likelihoods of marine heat waves, and the deep blues are very low likelihoods. So you can think of this just like a weather forecast, where basically there's a whole bunch of climate models being run every month, predicting what's going to happen for the next 12 months. And we take the output from these models and we classify as to whether they're predicting the marine heat wave or not. And then this is basically showing you the percentage of models that are saying yes or no for marine heat waves. So just like, looking at whether it's going to rain tomorrow. Instead, you're looking at whether there'll be a marine heat wave over the next year. So this is the forecast for this month, basically. And then if we look out 3 months, so looking out to December, then this is what we see. There's sort of La Nina conditions going on right now. So this is why you see along the equatorial Pacific, the eastern equatorial Pacific, very deep blues and low likelihoods of marine heat waves. But much of the North Pacific Ocean and actually the North Atlantic too have currently and predicted pretty high likelihoods of marine heat waves. Starting in 2023, to go along with these forecasts being available online, we added this heat wave discussion. So every month we provide this summary of what's going on globally, highlighting some specific areas, and also placing these heat waves in context with the historical record of how unusual things are at any given moment. All right, so we know that we can make the forecast, but a reasonable question would be, how good are the forecasts? And fortunately, with these climate models, we have over 30, in some cases now 40 years of forecasts that we can look at retrospectively and evaluate against what ultimately did happen to see how well the forecast did or how well the forecast would have done. And so this image is illustrative of that kind of analysis. This is looking at forecasts for what's going to happen 3 months later. And basically, the deeper the red, the better the forecasts. If you get to something that's very close to white, then you're not really doing much better than a random guess. And if you're getting to very deep reds, then you're basically right all the time. And what you see is that over much of the global ocean, there are fairly deep reds. And actually, the sort of thin black line that's outlining the deeper reds is a line for significance. So anything bounded by that line, we can be very confident is actually giving us some additional accuracy in these forecasts. So like the entire Eastern Pacific Ocean, our whole US West Coast and Alaskan coast, much of the tropical Atlantic and Indian Ocean and Southern Ocean, we see elevated skill at 3 months ahead. If we look at other forecast horizons, so 1 month ahead, you see even more of the ocean, obviously, with higher skill. And basically the pattern stays the same, but just skill overall declines over time. So when you get 6 months ahead, now you've got less of the ocean where you're really able to accurately predict heat waves, but you still do get areas like the US West Coast, the tropical Pacific, where you even 6 months ahead can predict these heat waves with some good confidence and some really good accuracy. So the beauty, I think, of my position, as Katie quickly mentioned, that I work between two parts of NOAA. I work between the OAR, Oceanic and Atmospheric Research, and Fisheries. So I really focus on not just the science behind these products, but also how they're useful on the fisheries side. And my fisheries colleagues are wonderful to work with in this respect, where we can take something like this and then say, okay, how can these forecasts inform management decisions? How can we get better economic and environmental outcomes by using the information from these forecasts? And there's a lot of answers, I think, for marine heat waves. It can inform better monitoring. It could inform how you handle tourism. If a coral reef is in danger of bleaching and you want to handle the impacts on the coral reefs. And what we think about a lot is fisheries management decisions, which again, there's many flavors of those that one can imagine, but I'm going to walk through two possibilities really quickly. So one of them is this tool. It's called TOTAL, which is an acronym for Temperature Observations to Avoid Loggerheads. This was developed, led by my colleague Heather Welch here in NOAA. And the idea here is that there's fishing that occurs off Southern California, and you might target something like swordfish, but be concerned about bycatch or catching things you don't want to catch. like endangered and protected species, one of which would be the loggerhead sea turtle. And so this tool basically says when it's warmer than normal off Southern California, there's a higher likelihood of loggerhead turtles being in the area. And so there's a higher likelihood of interaction with fisheries that are unwanted. And historically, one fishery, the drift gillnet fishery, has been closed down in the summer when it's expected that there will be an increased risk of interactions with loggerheads in the Southern California bight. So Heather did this more in-depth analysis to see if we could quantify at what threshold those risks of interactions with the fishery are more likely to occur. And she came up with this indicator, this total, which is based on the temperature in the Southern California bight and is shown as the black line. There you're seeing about 25 years of temperatures in the Southern California bight, some spikes around 98 and 2015 and 2016. And then in red, you see when there are observations, either there was bycatch or there are observations of loggerhead turtles in the Southern California bight. In 2015 and 16, you see some really big red dots. There are some harder to see ones that are back in the early 90s and in around 97, 98. But the point is that nearly all of these red dots are above this green line. So this is the threshold that Heather came up with as an indicator above which we are at much greater risk of catching turtles in these nets. And so in this tool, you would say, okay, we're predicting that the threshold will be exceeded, and this would be a good time to take measures to avoid interactions. So that's one, the total tool. Another one is the habitat compression index. Another one that came out of Fisheries here, led by Isaac Schroeder. And so this one was motivated by the whale entanglement issue that I mentioned earlier, and I can talk through a little bit more here. So on the bottom here, you're seeing a time series of whale entanglements off the West Coast in these bars. And the main point here is that there's this big spike in 2015 and 2016 to the right of this plot. On the top, what you're seeing is temperature over 4 years, 2013, 14, 15, and 16. And this is reiterating a point from earlier, but if you look at 2013, there's a fairly big area in blue, right? And this is that rich, productive water along the coast. As you go to the right, moving to 2016, you can see that a lot of that area goes away and turns orange and red. So this is the habitat compression. And this habitat compression index basically quantifies that. What is that area over time? And the lower that area is, the more compressed the habitat is. And we have this elevated risk of seeing whale entanglements. So both of these have can clearly be useful inputs to management measures to avoid catching whales and turtles. And so then the question is, can we predict these? And what we find is that the ability to predict these two indices is basically the ability to predict heat waves, because in both cases, you are really looking at extreme warm temperatures that you're trying to predict. So this figure is showing the observed habitat compression index in the sort of blue-green color, and then the pink, or sorry, other way around. The observed is the pink, and the forecast is sort of the blue-green color. This is only forecasting 1 month in advance, which is probably a useful amount of warning, but is not much in terms of like the scales that we think of when we're making forecasts a year in advance. But I can say that, you go several months out, you can still predict this habitat compression index very well. And again, the low numbers is what we're worried about here, where whale entanglements are more likely with a more compressed habitat. And then we have the total tool. And similarly, if you look at the two lines, they're tracking each other pretty well. And you're looking especially at when they exceed the horizontal lines, because that's when this alert would be triggered. And so here we're actually looking at a 6-month forecast. So giving notice 6 months in advance. And the closures historically here have been activated in the summer, in June, July, and August. So this would be, giving a prediction at the beginning of the year to try to understand what's going to happen in the summer. And actually, we did do that this year. We give a report, an ecosystem status report that we develop every year. We deliver it to the Pacific Fisheries Management Council. And this year, in that report, we included our prediction, which happened to be very low likelihood of entanglement risk. So to sort of sum that up, there was persistent habitat compression and high bycatch risk during that 2015-16 period. Both of those, with the forecast that we now have, would have been predictable months in advance. And that's not the only isolated incident that's predictable. In general, these kind of environmental drivers are quite predictable associated with marine heat waves. So now the real work is continuing to work with our partners in management, with industry, with the states, to try to get this information activated in the decision-making space. And with that, I'll thank you for your attention. Certainly feel free to reach out to me. I'll take questions now, but feel free to reach out to me. And at the bottom there is the URL for the marine heatwave page on the NOAA site. These forecasts are there, but also there's a whole bunch of other resources there on marine heatwaves. On the landing page, actually, you can see the current state of marine heat waves, which in the North Pacific is pretty dramatic. There's a huge marine heat wave out off our coast right now. So please check it out, and yeah, I'll take any questions. Thank you.
Awesome. Thank you, Michael. I'm going to flip us over to our question and answers and ask if you want to come back on camera, and
Yeah.
we'll get our questions going. So, our first question is a little long, so bear with me. I noticed there was an in season gillnet closure in Southern California Bight in 2024. And if you know this, do we have data for turtle bycatch showing that the closure was effective?
Ooh. I don't, but I don't think if the fishery is closed, we wouldn't have had bycatch. But certainly colleagues would have data to compare across the years. I think in 2015-16, I think there were closures enacted. But the main thing is that the lead time for those types of closures could be much expanded with these forecasts. So right now the decision is made, if it's looking really warm right before the summer, then that decision can be made. But the aim here is to give the managers and the industry heads up that, hey, maybe several months from now, this looks like this kind of closure is really likely, and action could be taken to prepare for that.
Okay, thank you. Next question. Why do you think the marine heat wave forecasts for the east coast of the US are low? Do you think using regional, I'm going to say MOM6 because I'm not sure of acronyms, model could improve the forecasts on the east coast?
Yes, this is either a very educated member of the general public or someone with inside knowledge. So MOM6 stands for Modular Ocean Model 6, version 6. And that's actually an exciting sort of motivator for talking about new developments that are coming. So we've used these global models for this first sort of iteration of these heat wave forecasts. But on regional scales, one could imagine much finer resolution, sort of more detailed forecasts with models that are specific to certain regions. And there is an initiative that's ongoing right now in NOAA called the Changing Ecosystems and Fisheries Initiative. And under that initiative, there are really high resolution, state of the art ocean models being developed along all US coastlines. And the whole idea there is to improve the performance of forecasts relative to the global models in order to better support decision making. So to actually answer this question, the East Coast, one of the reasons that the forecasts don't do as well on the East Coast is because the West Coast has El Nino and La Nina. It has the El Nino Southern Oscillation, which is a massive signal that provides us with a lot of predictability. And the East Coast is just not impacted by that big predictable climate signal in the same way. And it also is just a very dynamic region with like Gulf Stream meanders and things like that that can make big temperature anomalies pop up really quickly and not stick around. But there is a paper led by Andrew Ross, who's from NOAA as well, from GFDL, where he has looked at forecasts using this regional MOM6 model and has found improvements in predicting surface and bottom temperatures. And I'm not sure if he's looked at marine heat waves specifically, but I have no doubt that the improved performance on temperature prediction generally would translate to better marine heat wave predictions as well.
Awesome. Thank you. Okay, this one was asked twice. I think they just put it in twice. But talking about the El Nino Southern Oscillation, it's predictable a few seasons in advance, and the related temperature anomalies in the tropical Pacific have impacts felt elsewhere in the global ocean. How much of the skill in heat wave predictability is traceable to the El Nino Southern Oscillation?
A lot. Yeah. That's the quick answer. A lot. It's the two biggest things are one is persistence. So that is just things are for a while going to stay like they are now. And that's actually a real benefit in ocean prediction relative to predicting the atmosphere is that the ocean it evolves much more slowly. It has much more inertia, and so it has much more persistence. So just the fact that things are currently cold or things are currently warm tells you a lot about whether a marine heat wave is likely to come up soon. But yeah, next to that, ENSO is the biggest source of predictability. And certainly gives us months of lead time for the areas that are strongly impacted by and so when I showed those maps of how good the forecasts are, and like the Eastern Tropical Pacific and the U.S. West Coast and some of these places lit up, people who know the fingerprint of El Nino and La Nina would have probably seen right away that, oh yeah, that the performance of the forecast looks like ENSO basically.
Okay. Now, here's a question I do have also. What is the temperature threshold for a heat wave? So, how many degrees above average? How deep in the water column do the anomalies extend?
Yeah. So, what exactly is a heat wave has been an ongoing topic of discussion in the marine community for a decade. But most widely accepted way to define them is they're relative to a location. So, there's not an absolute temperature like 90 degrees Fahrenheit is a heat wave or something like that. It tends to be the warmest 10% um, of times in a specific location. So, if it's December here in California, if it's the top 10% of Decembers off California, then that would be a heat wave. And so you can imagine that wherever you are, that number is going to be different. Um, it could be in some places it might be as small as like a half a degree or a degree, and in some places it might be several. And then heat waves do occur everywhere, actually, also by that same definition. They occur everywhere in the water column. So there are bottom marine heat waves. One of my co authors, Dylan Amaya, has led work on those. Um, so heat waves that occur along the ocean bottom, and they've gotten a lot of attention because a lot of our most valuable species live on the bottom of the ocean. But they aren't necessarily the same heat waves that are occurring on the surface. So, like this one, the blob, um, when it first formed, it might have occupied the upper 50 meters or something like that of the ocean. But I think one of the reasons it was so impactful was that it stuck around and ultimately penetrated like several hundred meters deep. But you can have cases where something happening on the bottom is disconnected from what's happening on the surface. So there's a heat wave on the bottom and not on the surface. Um, which is a good reason to use things like models and also make sure we have assets in the water to observe those things directly that we can't see from the surface.
Okay. And I think this might be our last question, and that's good timing. Is it possible to use this? And I think you've said this, it is, but use the predictive information to make surgical fishery closures.
Yeah, that's absolutely what we're after, and that's a good way to say it to make it more surgical, because it's not like, maybe I conveyed that all we're trying to do is save whales and save turtles or something like that, but in NIMS we're trying to balance economic and environmental outcomes. So the idea is like a lot of fisheries have been probably closed, not only sort of left open at times where it might be dangerous to have them open, but closed at times where it's unnecessary. And so the whole idea here is that when you incorporate this environmental information, you can be more surgical with how you apply things like closures, both leaving them open when the risk is low and then closing them when risk is high. And again, hopefully improving both the economic and the environmental outcomes.
Great. Thank you so much. Okay, we are at time. So I want to thank Michael. I want to thank Dan from earlier. And I hope everyone has a safe, wonderful rest of your day. We are at time. Thank you, Michael, for a delightful presentation.
Thank you.
Take care, everyone.